All right, I'll begin. Dear Father, we thank you for this day. Thank you for the lovely weather outside. And thank you for the students. Just pray that you'd guide our thoughts today. Help us to, again, Lord, glorify you in what we do. In your name I pray, Lord Jesus. Amen. All right, so there's a lot of different ways you could organize this course, you know. So I think what we've done so far naturally goes at the beginning. And if you look at it, more or less we've covered chapters 1 through 6 of your book. Chapter 5, maybe not so much, right? There's some things on systems of differential equations and operators in there, if I remember right. So at this point, we could go and we could talk about systems of differential equations, but rather than doing that, I chose to, talk about series methods at this point. We could do that later. I mean, there's a lot of choices here as how you could approach the material. Anyway, I chose the path that we did, so we're on to series methods. So series, power series in particular, but not just that. So let me remind you what is a power series. So what is a power series? Power series centered at x naught with coefficients a naught, a1, a2, ... has the form what? Something like this, right? The sum k equals 0 to infinity of a sub k x minus x naught to the k, right? This is a power series. We call this thing f of x just to give it a name. So a power series is a function which is defined pointwise by a numerical series, right? So these are very interesting things. What's the connection, of course, between, for example, what happens when we plug in, let me write this out in a little bit more, you guys remember, a naught plus a1 times x minus x naught plus a2 times x minus x naught squared plus ... right? So we can also express it in terms of the first 3 terms or however many terms you like, right? What's the significance of the coefficients? Do you guys remember? How's it work? If we look at f of x naught, what's that equal to? What happens? That's 0. 0, everything's 0 except for this thing, right? So the 0th coefficient is the value at the center of the series, right? If I was to calculate f prime of x, what would that be? Let's see here, f prime of x is what? Now there's a beautiful theorem that I won't prove in here, and I probably won't prove in calculus 2 either. Where would I prove it? I don't know, somewhere else. And the theorem is this, which is that if you have a power series, you can differentiate term by term, right? So the derivative of a power series is simply, you can bring the derivative inside, basically, right? So, this, if you think, you can visualize it in your mind, there's a ddx before the infinite sum, we bring it inside. That's a non-trivial analytic step that takes a fair amount of doing to prove, but it can be proved that that's reasonable for power series. Power series are what are called absolutely convergent series on the open interval of where they converge. And absolute convergence allows you to do really nice things, like you can move the terms in the summation around without changing what it converges to. In contrast, if you have a conditionally convergent series and you move terms around, you can change the value to which it converges. All right, so those are less nice. But this is a constant, right? So it pulls out, and the derivative of the series is simply what happens to the 0th term? It differentiates to 0, right? And so we've got k, a sub k, x minus x naught to the k plus 1. Right. I've just differentiated term. Oh, did I say k plus 1? Grief. Sorry. I think it was grading those Calc 2 tests. They've worn off on me, some of them. And then, and of course we can express this. The first three terms are what? A1 plus 2a2, x minus x naught, plus dot 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 dot. I'll even do the next one. 3. Oh man, this board's a mess. 3 times. I forgot to bring my stuff as well. So you can see then, of course, that f prime of x naught is what? If you just think about plugging x naught into this, everything's 0 except for the first term, right? So f prime of x naught is a1, right? And we can continue down this path. What's f prime prime of x naught? What's f prime prime of x first? F prime prime of x is the sum k equals 2 to infinity, k times k minus 1, a sub k times x minus x naught to the k minus 2, which, by the way, is equal to like 2a sub 2 plus 3 times 2a sub 3 x minus x naught plus dot 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 dot. Right? So you can see that if you plug in x naught into that, what do you get? Right. Continuing in this fashion, what do we get? The kth derivative, right, at x naught is just equal to what? It's equal to k factorial times a sub k. And so, modulo a little bit of analysis that we're skipping over, we have shown, thus, a sub k is equal to the kth derivative at x naught over k factorial. In other words, f of x is equal to a sum k equals 0 to infinity of the kth derivative at x naught over k factorial times x minus x naught to the k. You may recognize this formula. What is it? Whose theorem is it that you can take a function and, given certain conditions on the function, represent it as a power series centered at a point in its domain? Yeah, this is Taylor's theorem. So Taylor's theorem isn't quite this, but it's with some fine print, this is Taylor's theorem, although I'm cheating a little bit, right? Because I'm starting with a power series and just showing you what the meaning of the coefficients is. Taylor's theorem says something a little bit more exciting. It says you can take a function, which isn't necessarily represented as a power series, and you can represent it as a power series, provided, certain conditions are met. All right? And those conditions are so benign that, they're pretty easy to meet. All right, so let me, oh man, see, this is what I get for not. See, the one day, I already know this stuff doesn't really work. Well, in my eyes. The reason I know it doesn't really work is because somebody cleaned the board with it before, and the board's already a mess. So it doesn't really leave a slick board after it. It's just environmentally friendly garbage. Come on. All right. So, let's see here. There's a, I'm being a little bit sloppy here in terms of telling you when this works, right? If you look at, we're in chapter 8, technically, and so he actually has some of the theoretical details in here, like he mentions on page 429 that if you calculate the Taylor polynomial, basically, there's a theorem due to Lagrange, which says that f of x is equal to the sum, all right, let's say k equals 0 to n of the kth derivative at x naught over k factorial times x minus x naught, all right? That's not f of x. F of x is, this is not f, this is the kth Taylor polynomial, all right? Then if you look at f of x minus this kth Taylor polynomial, in other words, this polynomial approximation to the function, that you can bound the error in that as follows by this is equal to en of x. He calls it little epsilon n of x, and the theorem is that. And I have a proof of this in detail on my Calc 2 notes if you want to look at it. There's some, let's see here, for x near x naught. I wasn't going to get into all this, but I just worked myself into a corner. So you can write the k, let's see here, n plus 1th derivative. At some point, let's call it c instead of Greek. So basically, and this c so that's again page 429 of your book has a little bit more build up to this, but basically what this says is that if you calculate the kth Taylor polynomial for a function, right, it's going to be pretty close to the function up to the next term you haven't included, right? The next term in the Taylor series that we haven't included would be this thing, right? So this is kind of akin to the alternating series estimation error test that you may be learning Calc 2, where you learn that, you know, if you take an alternating series up to term 4, then the error in taking the first 4 terms is basically as big as the 5th term. This is essentially saying the same sort of thing for the Taylor polynomial itself, without any sort of, you know. But that's basically it. So in order to show that the function is represented by its power series, right? I mean, there are functions for which you can calculate the Taylor series for, and yet the function isn't matched by the Taylor series. So, you know, here's a definition. If f of x is equal to the sum, let's see here, k equals 0 to infinity of, you know, the kth derivative at x naught over k factorial times x minus x naught to the k, for each x in u, right, then f is analytic on u. So what I'm saying is that if the function is represented by its Taylor series on u, then it's analytic on u. There are actually functions which are smooth, all right? Smooth means you can calculate as many derivatives as you want, and yet they're not analytic. Like here's the standard example, counterexample, function's not analytic is this thing. What you do is you take a function which is just 0 here, and then it's really, really smooth. It like does like this kind of deal here. The formula for this thing is something like this. F of x equals to 0, x less than or equal to 0, and it's e to the minus 1 over, I think, x. I think here. Maybe x squared, I forget. I can't remember if it's x or x squared for x greater than 0. Oh, just a second. He had that in here too. I'll tell you in a second. He might have. I don't know if he included it as a homework problem or if he had it in the body of the text. I saw it when I was looking. Where did he stick that thing? You could ask me, is there another example of a function which is smooth but not analytic? I don't really have another good example. They're all kind of more or less like this. And I've asked people who know more, if they have other examples, and basically what I get back are plays on this or really complicated things. In other words, this is really good news. I can't find the stupid thing. Anyway, so the point is, if you focus here on 0, right here, all right, here you get tk of x is just identically 0. Because when you calculate that thing, the derivative exists at 0. What is it?
It's on the previous one, so if you want to put your comments.
Oh, okay. So if you calculate the Taylor series here, in other words, you differentiate the function, you plug in 0, you can show that the derivative, of course the value of the function is 0, f of 0 is 0 by definition. You can show that f prime of 0 is 0. You can show that f prime prime is 0. It involves left and right limits. It's tedious to actually go through the details. But it can be shown that this function has derivatives and second derivatives and third derivatives and fourth derivatives and fifth derivatives of all order being 0. Which means that the Taylor series generated at 0 is identically the 0 function. So if I was to graph the Taylor series, it would look like this. Right? So there's no neighborhood of 0 on which this function is analytic because the Taylor series is 0 and yet the function is not. So this is like the example of a function which is smooth but not analytic. All of the functions we'll talk about now that we're past this introductory little talk will be analytic. Sine, cosine, exponential, logarithms where we're interested, inverse tangent, all of our favorite rational functions. These will all be analytic where they are analytic. In other words, where the functions behave. What's your question, Luke?
Okay, on your theorem of the a minus e sub k of x equals e sub x.
Oh, there's a k missing there. Is that what you're asking? This is supposed to be okay. Or something else?
On the second line, actually, I was wondering what the n is. So we just
Oh, yeah. Either I need to change those to k's or I change this to n. I'll change that to n. It's easier. But actually, so that is, oh my goodness, it's bad. This should also be an n. Sorry. Thank you, Luke. These are very good questions. Excuse me. All right, anything else I've said that's crazy? Those are important fixes to make. Yeah, thank you. The point, anyway, is that we can take a function and we can approximate it by an unending polynomial provided that the function's analytic. We can obtain as good an approximation to the function as we like. This is what Taylor's theorem says. Right, beyond the tangent line, there's a best quadratic, there's a best cubic, there's a best quartic, there's a best quintic. There's a best, I don't know the name for a sixth-order polynomial. I don't know. But okay, so that's the context. All right, this is the toys we have to play with. We have these functions. They're analytic. We can start looking for analytic solutions to differential equations. All right. Before I actually solve any differential equations, though, let me just give you a quick rundown of the standard examples we know of series from Calc 2, because we need things to work with, right? So what are the tools in our toolbox, so to speak? So known examples. In other words, these are things I want you to know. I guess I'll give you a 3x5. Well, wait a minute. I can't commit to that yet until I grade your test. Once I grade your test, I may not commit to giving you a 3x5 card on the next. It depends on what I see. But let's be optimistic. I probably give you a 3x5 card for the next test. The first and most important example is this one. This is what the geometric series converges to. So this is equal to a plus ar squared plus dot 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 dot. Provided that the magnitude of r is less than 1. From this, we can get stupid amounts of examples. Like, let me show you. Simple one. something like x over 1 minus x squared. What is that equal to? Well, that's equal to, so here I identify a is equal to x, r is equal to minus x squared, right? So this is the sum k equals 0 to infinity of a r to the k. That's what this looks like in summation notation, right? And so that in particular is the sum k equals 0 to infinity of x times x squared. Parentheses are our friends. Do not discount them. So then cleaning that up, this is what the sum k equals. So what I'm doing right now is sigma notation, right? If I ask for an answer in sigma notation, I mean what I'm doing right now. X to the 2k plus 1, all right? Some answers I'll ask for like the first 3 terms or the first 3 non-trivial terms. Sometimes I would ask for sigma notation. It depends on the problem and how mean I'm feeling. No, just the problem. I'm always mean. Let's see here. Sorry, I like the way that came out. X over 1 minus x squared is that power series, right? Where? For what x?
The magnitude of x is less than 1.
Right. So this is just for another example. If I have 1 over, say, 3 plus x squared. One over 3 plus x squared, what would this be? Well, see, this 3 is cramping our style. We got to factor it out, right? So this is 1 over 3 times 1 plus x squared over 3, right? So if you tilt your head and squint, you can see either you can look at this as 1/3. I mean, I'll do it this way. 1/3 times the sum of what? X over, well, x squared over 3 to the power k. So my r, my ratio for this geometric series is x squared over 3, right? So the absolute value of r being less than 1 is the absolute value of x squared over 3 being less than 1, right? But what's that? That's the same as the absolute value of x squared being less than 3, aka the absolute value of x being less than the square root of 3, also known as minus root 3 less than x less than root 3. No equality. When the ratio is equal to 1, it's not ambiguous what happens to the geometric series. It's just, it's dead. Ratio equal to 1 makes geometric series diverge without qualification. It's just dead. It diverges. And if it's minus 1, it's no better. It fails by the kth term test. I do assume you know some calculus too. So this shows us that the interval of convergence is in interval notation, which seems like a good idea for interval of convergence, huh? Minus root 3 to 3. Root 3. That's the so-called open interval of convergence for this series, which also happens to be its interval of convergence because both endpoints diverge in this case. Right? So far, so good? Can you integrate that? What's the integral of dx over 3 plus x squared? Well, I will tell you what it is. It's 1 over root 3. Inverse tangent, or arctangent, if that's how you like it. X over root 3 plus a constant. Fine. That is the integral. You can factor out a 3 and make a u equals x over root 3 substitution if you like. That gives you integral of 1 over root 3 du over 1 plus u squared. So then that integrates the inverse tangent of u times 1 over root 3, but u is x over root 3, so that gives you 1 over root 3 inverse tangent of x over root 3. Or if you don't like that, you make a trig substitution. Anyway, that's the integral. But on the flip side, we can integrate term by term, right? Now I got to be careful here. I need to convert this to a straight up power. This is not a power series, by the way, right? This right here is not a power series. This is something else. Not yet, anyway. I would say this becomes a power series when I do a little bit of algebra and I rewrite it as a coefficient, which is 1 over 3 to the power k, times x to the 2k. At this point, I would say, okay, that's a power series. It has to be a power series before I can do my term-by-term calculus, okay? So what I have then is I've got the sum k equals 0 to infinity of 1 over 3 to the k plus 1. The k plus 1 is because I'm multiplying the 1/3 times the 1 over 3 to the k. All right? Multiplying these together to give me that. And what does x to the 2k integrate to? Plus 1, right? Sorry, my font is mismatching. And then I should add a constant, I suppose. Right. So let's collect our thoughts. What do we have? We have that 1 over root 3, right? Inverse tangent of x over root 3 is equal to what? It's equal to some constant plus this series, sum k equals 0 to infinity, and I've got 1 over, let's say, 3 to the k plus 1, parentheses 2k plus 1, all times x to the 2k plus 1. So how do I figure out what the constant is? But that, well, I guess I could, but the point of this is to not calculate. You don't want to calculate the Taylor polynomial for the inverse tangent because the first derivative is okay, but the second derivative is not, and the third derivative is worse, and the fourth derivative by then is just awful. I mean, you're differentiating a quotient after the first derivative. You don't want to do that. That's the point of this, is that we don't have to calculate by taking successive derivatives if we use the building block of the geometric series and term-by-term integration, or my next example, term-by-term differentiation. You should have seen these things in calculus too, but people forget these things. That's why I'm going over them with you guys again now, because it's important that you know these. So I would just plug in 0 personally. I mean, inverse tangent of 0 is something I know, right? And this series is very easy to understand when I plug in 0. What happens to the series when I plug in 0? What's the first term in the series? K equals 0 gives me x here. Right? So when I plug in 0 into x, it's 0. When I get to k equals to 2, it's x cubed. That's still 0. This whole series is 0 when we plug in 0, when we evaluated 0. So plugging in 0 gives me that we have 0 is equal to c. So this problem's pretty forgiving. If you didn't add the constant, you wouldn't have gotten into trouble. Okay. So in short, we have then that the inverse tangent of x over root 3 times 1 over root 3 is equal to the sum k equals 0 to infinity, 1 over 3 to the k plus 1, 2 to the k plus 1, x to the 2k plus 1. So there you go. There's a power series expansion for that inverse tangent with a weird argument. So like, a fun question. What's the 50th derivative of inverse tangent at 0? If I call this thing g of x, what's g, the 50th derivative at 0? And what's the 51st derivative at 0? Well, inverse tangent is what kind of function? Is it an odd function or is it an even function? Or is it neither? Right. So inverse tangent's odd, and it's no accident that it has an odd series. Odd functions have odd power series. Even functions have even power series. This is very useful as you're trying to think through what you should do and checking yourself on things, right? But you can see odd, right? So what that means is kind of sneaky. 50 is even. There is no even term. That means that going back to Taylor's theorem we stated a minute ago, with x not equal to 0, the 50th derivative is 0. So that's just 0, because there is no even term to have 0. Now, in order to get the 51 here, I would need this to be 51, right? And so, in other words, this is equal to, dot, 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 plus the 51th derivative at 0 divided by 51 factorial times, x to the 51 power, and plus stuff. Okay, there's stuff before, there's stuff after, but that's the one we're interested in. And power series, like polynomials, have to have matching coefficients. So whatever's the 51st thing in the Taylor, I'm sorry, I should use G here, because I'm talking about G. Whatever's the 51st term in this expansion has to be the 51st term in what we get from Taylor's theorem. You shift it over? Can we see it? So, in short, I put k equal to what, 25? So I get 1 over 3 to the 25 plus 1, 26, times, that's 51, right? Is equal to the 51st derivative at 0 over 51 factorial. So in other words, the 51st, I keep going back to f, g, the 51st derivative at 0 is equal to, 51 factorial divided by 3 to the 26th power times 51. You could simplify this, of course. That's 50 factorial divided by 3 to the 26th. I don't recommend trying to figure that out by direct differentiation, right? So, yeah. The what? The what?
You do G51 of x?
No. Oh, G51 of x would just be, of x, well, I mean, of x. I would just take this and just differentiate it 51 times. I mean, that would not be, yeah. I have the connection between the coefficients and the values of the derivative and second and higher derivatives of the function at the center of the series. But I have information about the function's value and the value of its derivatives at that point. The interesting thing is those values determine the behavior of the function near the point on its open interval of convergence. Whatever happens at the center completely describes how the function behaves everywhere else. It's really neat. Well, I think that's a good amount of this. Let me, we could also look at how you could do something like, I'll give you some homework on that to refresh your memory. How about that? Yeah. Let me get to our standard examples. Geometric series is a huge, it's an example builder, as I hope I've convinced you a little bit of here. There are other things, though, we already know. Principal among those, e to the x is what? It's 1 plus x plus 1/2 x squared plus 1 over 3 factorial x cubed plus da da da. In summation notation, that is the sum k equals 0 to infinity of x to the power k over k factorial, right? The cosh, e to the x, remember, is cosh x plus sinh x, right? These are the even, and these are the odd terms in that exponential series above. In other words, cosh x is exactly the sum k, let me use j. J equals 0 to infinity of x to the 2j over 2j factorial. And sinh is the sum j equals 0 to infinity of x to the 2j plus 1 over 2j plus 1 factorial. If you look at that, though, those are exactly just the even and odd terms in the exponential series, split into two pieces, the cosh and the sinh. Right, so this power series for cosh, power series for sinh, power series for exponential. You can derive these from Taylor's theorem, right? And then let's look at e to the I theta. What is that going to be? That would be the sum k equals 0 to infinity of like what? I theta to the k divided by k factorial. How's that work? Well, yeah, but I guess we need to figure out what is I to the k. So let's see here. Well, any sum you can break into four pieces. Let me show you this. I can break this into the sum j I theta to the 4j over 4j factorial plus the sum, oh, I shouldn't do this. No, I shouldn't do this. It's a bad way. Let me not do that. That will just confuse you guys. So look at this. I is I, right? Well, I to the 0 is 1, okay? I to the 1 is I. What's I squared? It's minus 1, right? I cubed is what? It's minus I, right? So if you look at this, your idea to split into real and imaginary parts is a great idea. I would point out that and that continues on, right? Like I to the 4th is what? It's 1 again, right? So powers of I work mod 4. If I add any multiple of 4 to the power, I'm back where I started again. But you can see that I can split off the even powers, right? So I've got like the sum k, well, let's use a j. J equals 0 to infinity of I theta to the 2j over 2j factorial plus the sum j equals 0 to infinity of I theta to the 2j plus 1 over 2j plus 1 factorial. What I've done is I've split it into the even and the odd parts of the series. Does that make sense, that step? And the reason I'm doing that is because I know that's going to give me the real part and the imaginary part from this calculation I did with I. Like I expect that. So what's the deal with I to the 2j power? Can you simplify that? I would argue that that is actually minus 1 to the j, theta to the 2j, over 2j factorial. And this is actually plus I times the sum, minus 1 to the j, theta to the 2j plus 1, over 2j plus 1 factorial. Let's see if I can convince you of that. What is I to the 2j? Let's see here. If j is like 0, or if j is 4, let's see here, j is 0, j is 2, j is 4, j is 6. What do we got? Like, what's I squared? I to the 0 is 1, right? I to the 4th is what? It's 1. I to the 8th is 1, right? But this is like j equals to 2. This is j equals to 4, and so forth, right? So if j is even, it's 1. If j is odd, so like I squared minus 1. I 2 times 3, I to the 6th minus 1. So it's minus 1. If you just look at the cases, this I to the power 2j becomes minus 1 to the j. And similarly, I to the power 2j plus 1, this is a claim I'm making, I to the 2j plus 1 is actually equal to I times minus 1 to the j. For example, if we look at j equals to 1, we get I to the cubed, right, which is I times minus 1, right? To the what? To the 1, right? Because I cubed is minus I, right? If you look at, if you look at j equals to 2, you'd have something like I to the what? To the 5, which is I to the 4th times I, which is just I. All right. Now, the beautiful thing, of course, is that this power series right here is exactly the power series for cosine, and this right here is exactly the power series for sine. And so this is a way to derive Euler's formula that I stated for you before, right? So we look at we take the power series for the exponential, we evaluate it at I theta, use the fourplicity of the imaginary unit to break it up into the real and the imaginary parts, and then lo and behold, that's cosine and that's sine. Of course, you can derive that this is cosine and sine by Taylor's theorem, by direct differentiation and evaluation at 0. You can derive these Maclaurin series for cosine and sine, like you probably did in Calc 2. All right, so we got power series for sine, cosine, cosh, exponential, and a lot of rational functions from the geometric series. What else do you guys know about series? Can you multiply them? Can you divide them? Did you? Well, all right. Well, I'll tell you what. We'll come back and do that as we need to. How about that? Any questions about this before I? All right. Do you guys remember how to decide what the interval of convergence is for a series that's given? What can you do to it? What tests can you use on it? I mean, there's a lot of different tests for numerical series. We got all those, the integral test and the comparison test and limit comparison and the root test and the this test and the that and the kth test and those are all for really numerical series. For power series, the go-to is the ratio test, right? The ratio test will tell you the interval of convergence, the radius of convergence. There's a careful statement of it in chapter 8. You can remind yourself what it is. It's on page. Where's that stupid thing? I found it earlier. I know it's in here. Yeah, 432 is where there's a nice statement of the ratio test. Now, the ratio test does let us down in certain cases. The ratio test, the ratio test is based on taking ratios of successive terms in the series. Small victory. I actually managed to say that word today. And so if you have a series which has bunches of 0 terms, then some other sneaky business is involved in terms of calculating the radius of convergence, but ratio test will get us pretty far. All right. Of course, you can do other things with known examples, right? But I'll give you some homework and let you work on that for yourself in the homework. I think I've spent enough class time on it at the moment. So, differential equations. What does this have to do with differential equations? All right. So here's the question I'll pose. How to solve differential equations with series. There's this beautiful theorem that says that if we have a linear differential equation, right, and if the coefficient functions of the differential equation for this linear differential equation, if those are all analytic, all right, on some interval, then I think I have to have the leading coefficient is 1 for this theorem I'm stating. So it has to be what's called monic, but then the solution exists and is analytic wherever the coefficient functions are defined. So it's kind of like garbage in, garbage out. So if I had something like, you know, I'm not going to solve this, okay, but if I had something like this, something like this, that theorem says there's an analytic solution to this thing, and it exists everywhere where the coefficient functions are analytic. Good news, sine of x is analytic on the whole real line, and e to the x squared is also analytic on the whole real line. Now, actually calculating the power series solution to this thing is quite awful. All right? I mean, I can calculate the first couple terms in it for you. Let me see how, it's a question of time. I want to do at least one non-trivial example for you. This is, yeah, okay, we got time. Let's calculate the first, is there a question? No? Okay, let's find the first, let's say 3 non-trivial terms in the power series solution to this centered at 0. This is an awful example to start with, but I already wrote it down, so I have to do it now. I've committed to it. Find first 3 terms in solution centered at x naught equal to 0. So what we're looking for is something like this. Y equals to a naught plus a1x plus a2x squared, right? Plus dot 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 dot. So let's see here. What's y prime? Y prime would be just a1 plus 2a2x. Y prime prime would be, you know, other stuff, but just 2a2. I'm being lazy. I'm hopeful that just writing these first 3 terms is going to allow me to find conditions on a naught, a1, and a2 to write down the solution. We'll see what happens. I may need to write down a next one. So what we're going to do is we're just going to plug these things, right? We're assuming that the solution has this form, and we're just going to plug it in there and see where it takes us. That's it. That's the method. You're like, what? That's the method? Yeah, that's the method. You assume the solution's a power series, and you shove the thing into the differential equation, and you calculate. So that gives me 2a2 plus stuff. Oh, shnikes. Oh, fine. I'll keep one more term. I feel my spider sense is tingling. All right, so that gives me 2 terms here, 6a3x. Hopefully just keeping to linear will work for me. Now, sine of x is what? That sine of x. I don't write sine x. Everything has to go into power series. That's the thing. Right? It's power series all the way down. Everything must be converted to power series to do this calculation. So sine of x is not sine x anymore. It's x. If you want minus 1/6 x cubed, but I don't really think we're going to need to go that far. I hope you guys know how to multiply series because we need to do it here. But it's not especially exciting what we're doing. So then the y prime is a1 plus 2a2x plus, 3a, 3x squared. I'm writing more than I need to, okay? That. And then e to the x squared. What's e to the x squared? Good news. E to the theta equals to 1 plus theta plus 1/2 theta squared plus da 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 implies that e to the x squared is equal to 1 plus x squared plus 1/4 x to the 4th plus da 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 da. Oops, I'm an idiot. There's a half here. You just set theta equal to x squared, right? You make a substitution. Can you substitute into series formulas? Oh, yes. Yes, you can. Will I prove that? No. No, I will not. Let's see here. 1 plus x squared plus 1/2. I mean, if I had like 4 less classes to teach, I could work the details out for you. Now, I certainly don't need to the quartic term. I just wrote it down for kicks. And that gets multiplied by y itself, right? Now, our experience up to this point has served us well. We have learned about equating coefficients and so forth, right? It's just now instead of having 3, 4, 5 undetermined coefficients, we have arbitrarily many. So the game got a little bit harder, but still the same game. So, all right, guys. No, but I did say that we were only playing this game up to order 3, right? So what do we do? Where should you start? I say we start by looking for constant terms. Is there any constant term in this? Because the constants on the left-hand side have to be equal to the constants in the right-hand side, which, by the way, are 0. So constants. I've got a 2a2 right here. This has got an x and an x cubed. This is dead to us. It's all multiplied by x. This here, you said 1 times a0, right? 1 times a0, that's it. There's 1. Our next equation, x. So we've got ourselves a 6a3. Let's see here, plus a1. What should we be expecting, by the way? What is this? This is a second order linear differential equation. The general theorems I stated earlier in the course are still true. The solution set should involve 2 linearly independent functions, and it should come packaged with like a C1 and a C2. There should be 2 undetermined sort of constants in the solution that reflect our ability to choose different initial position and a different initial velocity, if you like to think of it that way. So we're expecting to have 2 of these coefficients kind of parameterize all the other ones is what's going to happen. Is there anything else in x here? I got the 6a3. Oh, plus a1. Okay. How about x squared? There's something here I haven't written down. Got to be careful with that, right? What's the next thing here that I haven't written down? It comes from a4 x to the 4th, right? So there's a 12a to the 4, a4x squared here. So I'd have 12 a4. Where else do I have x squared? Plus what? Plus 2a2 from this times that, right? And that's it. Because the cube doesn't give you an x squared, right? It's not magic. It's stuck with 3 or higher. Over here, I have a2. I have a naught. Anything else? I see I got this times that, and I've got this times that. Is there any other way to get x squared from that product? By the way, how do you multiply series? The answer is just like polynomials, right? You just multiply terms of like order and collect them together. This is called the Cauchy product. if you define it carefully. All right, I think that's it. So let's collect our thoughts. What this tells me is that a sub 2 is equal to minus a sub naught over 2. That's my first thing. This tells me that a sub 1, well, this tells me a sub 3 is equal to minus 6, is equal to what? Minus 2a1 divided by 6, or if you like, minus a1 over 3. All right? And this one tells me that a4 is equal to, it's equal to minus 3a2 minus a naught divided by 12. But you see I can convert the a2 to a naught. This is really minus 3 times minus a naught over 2 minus a naught over 12, which is, excuse me, looks to me like 1/2 over 12 a naught. I think I get a naught over 24 there. Correct me if I'm wrong.
You said you can't just use summation notation to find a general formula for the nth term, just because it gets.
Oh, this one is not that, to quote my community college professor, that dog won't hunt.
Okay.
It's awful to do it directly in terms of summation notation, this one.
Okay.
If I haven't wasted too much time on this, I'll do one with summation notation in just a second. But
We have 5 variables.
aha, yes, what do we have? So in conclusion, we have y is equal to a naught. All right. What comes with a naught? Well, 1, right? There's a 1. What else is what? A sub 2 x squared, right? A sub 2 x squared. But what is a sub 2? A sub 2 is minus 1/2 a naught, right? So minus 1/2 x squared. And then I got an a4, right? If I haven't made a mistake in my arithmetic down here, which I'm a little bit worried about, 3/2 minus 1 is 1/2. Okay, I'm okay. 1/2, yeah, 1/24. So then plus 1/24 x to the 4th, and then stuff I haven't calculated. I can pull an a naught out of the even terms. The odd terms, I can pull an a1 out of. Now a1, of course I've got the 1 times a1, which just gives me the x, the initial x. And then a3 is minus 1/3 times a1, right? So that gives me minus 1/3 x cubed. So, sorry guys, I think I accidentally calculated all the non-trivial terms up to order 4. But there it is. And you could keep going, obviously, but I think that illustrates the method. Yeah? And as you can see there's 2 functions, right? We don't have names for these. So here's like my y1, right? Here's my y2. y1 and y2 form my fundamental solution set. They're just not elementary functions. They're functions that are described by series, of which I've only figured out the first few terms at the moment. But there's nothing stopping me. We could figure out more to your heart's content. You just got to keep multiplying and collecting terms and such. Now what Austin was telling me about was, are there other problems where you can do this calculation but exactly? In fact, there are. All right. If you got a question about this, you better ask pretty soon. It's going to start melting before your eyes. Oh man, come on. Sometimes they'll melt.